Okay, so welcome back. So I wanted to, we won't entirely finish chapter one today, but we'll get close to it. Well, maybe not. But anyway, uh, what I wanted to do is a couple of examples of something called parametric vector form, which is just a nice way of describing solutions to linear systems or matrix equations or vector equations, right? So let me get my nice, convenient theorem that I've boxed here. So from last time. So from last time, my very convenient boxed theorem is the following. Which says that whenever I see matrix equation ax equals b, that's the same thing as this vector equation, right, where I've written this matrix product ax as this linear combination. So the entries in the vector x are the weights in this linear combination, and these a sub 1s, a sub 2s, those are the columns of a. And so these two things are the same, and also these two things are the same. All these things are the same. So this vector equation has the same solution set as the linear system that has augmented matrix made up of all the columns of A, and you've tacked this B column vector on at the end. Okay, so that's nice because what that tells me is that whenever I see linear system, I can think of vector equation, I can think of matrix equation, and I can flip back and forth between any of those things. Okay, so what am I going to do here? Well, the idea, first of all, I have to make a definition. This is, if you have wondered why, so those of you that have had 246 or the equivalent, if you've had a differential equations course, you might remember that in a differential equations course, kind of one of the most, when you're taking your first ODE course, like one of the most important conceptual things that comes up is when you're solving, say, a higher order differential equation, so order 2 or higher, what you learn is that every single differential equation of that type, when you write out the general solution, it comes in two pieces. Okay, so if we're talking completely generally here, it comes in two pieces. So the first piece is the homogeneous part, which you'll know is easy to find in differential equations. And then there's the particular part, right? So it's homogeneous plus particular solution. If you've had differential equations, that's something that comes up over and over and over again. And you might wonder like why that is or where that comes from. Actually, where that comes from basically is linear algebra, because the same thing happens for us. It's not as big of a deal in our course. It's not as big of a deal in linear algebra as it is in differential equations, but it's still there, and that's basically why it's there. So here's a couple definitions. So first, a system of linear equations is said to be homogeneous. Okay, if it can be written as the matrix equation AX is equal to the zero vector. Okay, where A is just some m by n matrix, and obviously 0 is the zero vector. Okay, so if your system of linear equations can be written like this, it is a homogeneous equation. Okay. Note a homogeneous equation always has at least one solution. Okay. And you might be thinking, what is that? Well, if I take x to be the zero vector, this is a solution, right? You can just check really quickly that a matrix A times the 0 vector. So whatever the columns of A are, right, they are going to be multiplied by weights, which are all 0. So this is 0 A sub 1 plus 0 A sub 2, and so on. So all the way up to 0 A sub n. Whatever these columns are, it doesn't really matter. You're multiplying all of them by 0, summing the results. You're going to get the 0 vector. Okay. Okay. This solution is called the trivial solution. So this is called the trivial solution. All right. And so when you're discussing homogeneous equations, typically what is the thing of interest is to ask whether or not there are non-trivial solutions. All right, so typically the thing of interest for non-zero, or for homogeneous equations, I should say. I don't know what I'm writing there. Is whether a non-trivial solution exists. So we already know that the trivial solution always exists. So we're in the case that it is consistent. A homogeneous equation is always consistent. It always has at least one solution. The question is whether it has more than one, right? And of course, we know if it has more than one, it has infinitely many. But so the thing of interest for homogeneous equations is whether it has non-trivial solutions. That is, solutions that are not the 0 vector. This is the thing we're interested in, okay? For homogeneous equations. All right. Well, what does this tell us, right? So filtering through all of the things we know about, what we've done so far, the equation ax equals 0 has a non-trivial solution if and only if what happens? So it always has a trivial solution. Having a non-trivial solution means having more than one solution, i.e. having infinitely many solutions. How does that happen? Right? How do you have infinitely many solutions? It's that the associated linear system has at least one free variable, right? So this is if and only if the equation has at least one free variable. Okay. Okay. Now, here's a quick example. So determine if the following homogeneous system has a non-trivial solution. Okay, so what's the system? So this is 3 x sub 1 plus 5 x sub 2 minus 4 x sub 3 is equal to 0. And minus 3 x sub 1 minus 2 x sub 2 plus 4 x sub 3 is equal to 0. And 6 x sub 1 plus x sub 2 minus 8 x sub 3 is equal to 0. Okay. Then describe the solution set. Okay. All right, so let's do this. So the first thing we do is we set this up as matrix equation ax equals 0. But doing so, this just means my I mean, I can write this as Ax equals 0. It's clearly homogeneous. So then this has associated augmented matrix, which is just A and then the 0 vector column, right? Well, what is that? So that is my augmented matrix. I'm going to read row-wise. So this is 3, 5, minus 4, 0, minus 3, minus 2, plus 4, and 0, 6, 1, minus 8, 0, right? That's what it looks like. All right, so let's zero these things out quickly. So I'm going to add row 1 to row 2, replacing row 2. That's going to nicely zero out these two entries. So row 1 plus row 2 is the first thing I do. And then also I want to zero out this entry, which is I'm going to multiply row 1 by minus 2 and add it to row 3, replacing row 3. So minus 2, row 1 plus row 3. So what do I get here? So row 1 is unchanged by these two things. So it's 3, 5, minus 4, 0. Row 2, so I'm just adding these two rows, replacing row 2. So this is 0, 3, 0, 0. And then lastly, minus 2 times row 1 plus row 3, replacing row 3. I get minus 2 times 3 is minus 6, plus 6 is 0. I get minus 2 times 5 is minus 10, plus 1 is minus 9. Minus 2 times minus 4 is 8, plus minus 8 is 0. And then that operation on 0 just also yields 0. Okay, so this is pretty nice. I can then add 3 times row 2 to row 3 to zero out the last row entirely. So 3 times row 2 plus row 3 leaves me with, so I have 3, 5, minus 4, 0, 0, 3, 0, 0, and then 0, 0, 0, 0. Okay, so I've zeroed that out entirely. I can then scale this to be 1 if you like. So I'll do that first. So this is 1/3 times row 2. Leaves me with, in row 2, I have 1, or 0, a little bit off the page, 0, 1, 0, 0. My third row is all zeros. And then I can use this to zero out this entry above the 1 here. So that's, say, minus 5 times row 2 plus row 1, replacing row 1, because that's the only entry it's going to affect. So this would be 3, 0, minus 4, 0. And so to put this into reduced row echelon form entirely, might as well scale row 1 by 1/3. Right? This puts me into reduced row echelon form. So this is 1, 0, minus 4/3, 0, 0, 1, 0, 0, 0, 0, 0, 0. Okay, so I'm in reduced row echelon form. So I have to do the minimum amount of work here to write this out. So what does a solution to this thing look like? I want to continue on, so let me leave this here. There, that's good. Okay, so there's my resulting matrix. Okay, so then what does this translate to in terms of the system? This is x sub 1 minus 4/3 x sub 3 is equal to 0, and x sub 2 is equal to 0, and x sub 3 is free, right? So 0 is equal to 0 is what I get there. And so what I end up getting is x sub 1 is equal to 4/3 x sub 3, x sub 2 is equal to 0, and x sub 3 is free. This is how I would have written my solution before. But here is a nice way of writing this that we're going to use, and this becomes important after we discuss things in chapter 4, because we're going to define some quantities in chapter 4 that you will need to know how to write things in this form in order to express. Okay. So remember, someone's saying, can you consider x of 1 to be free instead of x of 3? So remember how this this works in terms of reduced row echelon form and the roles that that things are considered. So the way that we're doing this is, we're pushing the ones up to the top and to the left. So by the conventions of reduced row echelon form, the answer is no, to get us that uniqueness. Now, practically speaking, knowing what you know here, could you treat it that way, right? Like, forget about reduced row echelon form for a second. Could you treat it that way? The answer is yes, you could. Okay, but by the conventions that we've done, the free variables associated to the non-pivot column, right? So for us, the non-pivot column is the third column, and that's the free variable. The point is, if you wanted to do it in another way where you didn't care where the pivots were arranged, then the answer is, could you treat it in this other way? You could technically do it that way, although you'd have to redo how you do reduced row echelon form. You'd have to. There's a reason why we do it the way we do it. We do it because it gives us uniqueness to reduce row echelon form, and there's no benefit to considering one of these free over the other. So clearly here, the way that we've done it, like x of 3 is the free variable because it's associated to the non-pivot column. So that's why. Okay. Anyway, so this is how we've listed this. So the idea is I want to write out the general solution to this homogeneous equations. How do I do that? So the general solution is my vector x. This general vector x. So this is my general solution to ax equals 0 here. So my general vector x has entries. Oh, sorry. X of 1, x of 2. And x of 3. Okay. So my general solution has these entries. But according to this, I can replace these entries with what I have written here. So this is 4/3 x of 3. X of 2 is 0. X of 3 is free, which means that x of 3 is x of 3, and I have no other info. I'm free to specify that to be whatever I want to be. Okay. And in this case, I can write this in a nicer way where I can factor out that x of 3. So I can factor out that x of 3 in this way. So that this is 4/3, 0, and 1. Okay. All right. Okay, so what does this tell me? I've written this as a vector. You can call this vector v if you like. So I've written it as x of 3 times a vector v. This x of 3 I can think of as some free parameter, right? This is my free variable. This is the thing I have a choice of. What this is saying is that any solution to ax equals 0 for this particular problem is a scalar multiple of the vector v, which is 4/3, 0, 1. So this allows me to describe, say geometrically, the solution set here. Okay. A solution is trivial if it's the 0 vector. That's what makes it trivial. Okay. Yes, this is how you should write general solutions for the homework. Although, if I don't specify I want it in parametric vector form, you don't have to worry about it too much. But yes, ideally, this is how you write out general solutions. So this asks you to describe the solution set. Any solution is a scalar multiple of this vector. So another way of thinking about that geometrically is this vector specifies some point or some vector in in space, right? So 4, 0, 1. So if here's x sub 1, here's x sub 2, and here's x sub 3, then I have a point. So this is 4/3 0 x sub 3. So it's in the x sub 1, x sub 3 plane. So maybe here's my vector v. And then any solution lies on this line, right, in space. So geometrically, this is what's going on, but it's kind of better intuitively to just think about it as any solution is a scalar multiple of that vector. Okay. All right. Okay. So that's how this works. Okay. So now, in general, how do I write a solution to, say, non-homogeneous system in parametric vector form? So parametric vector form for a non-trivial solution. So or for a non-homogeneous system. So how does this work? The idea is that I have some equation ax equals b. So describe all solutions where a is 3, 5, minus 4, minus 3, minus 2, 4, and 6, 1, minus 8. Okay, and b is 7, minus 1, minus 4. Okay. All right. So notice this is actually the same is the same coefficient matrix that I had before. So I already know what this thing looks like in reduced row echelon form. I actually just have to keep track of what goes on with b using those same operations. So this is 3, 5, minus 4, 7, minus 3, minus 2, 4, minus 1, and 6, 1, minus 8, minus 4. So if I use a bunch of row reduction things, i.e. the same exact row reduction operations I used before, so same as before, since it's the same coefficient matrix, I just have to keep track of what happens in the b. So this gives me 1, 0, minus 4/3, minus 1, 0, 1, 0, 2, and then a row of zeros. Okay. All right, which leads to x sub 1 minus 4/3 x sub 3 is equal to minus 1. X sub 2 is equal to 2. And 0 is equal to 0. Again, which tells me nothing. Okay. All right. So now what do I know? Well, keeping this up here so you can see it. So this is what I got ultimately from all of my writing. So this means that for a general solution, x, which is completely general, x sub 1, x sub 2, x sub 3, from these equations, I'm told that this is equal to, x sub 1 is equal to, if I move 4/3 x sub 3 to the other side, I get minus 1 plus 4/3 x sub 3 in the first slot. In the second slot, I get x of 2 is equal to 2. And in the last slot, I get x of 3 is equal to itself because it's the free variable. Okay. Now, rewriting this, I'm going to split this up as vectors -1, 2, and 0. Okay. Plus 4/3 x of 3, 0, and x of 3. Okay, so I can break up this vector into the sum of two vectors. And now I want to do the same thing I did before, and I want to take this free variable and factor it out, treat it as a scalar multiple times a vector. So -1, 2, 0, plus x of 3 times 4/3, 0, 1. Okay. So here is parametric vector form for this general solution x. Okay. So here is a vector I'll call P. Here's the vector I'll call V. Okay. And here is my parameter. Here's my parameter, which is where the word parametric comes from. So this is my parameter. Okay, that is my real number. I'm completely free to choose that x of 3 to be whatever I want it to be. Okay. All right. So here's why it's called parametric vector form. This, I wanted you to see it written exactly in this way because really it turns out that if I have the equation x is p plus t v, where p and t are vectors and t is a real number, it's just generic parameter. What is this? Well, we know what vector sum looks like geometrically. Hold on, let me actually draw a straight axis. Okay, so vector sum geometrically means if I have some p here, so if I have p specified by this vector, v is some other vector here, it's not parallel to p, then v plus p I can compute as, of course, this third non-trivial vertex of that parallelogram. Okay. But then what am I doing when I add not just v to a vector p, but I add t times v? What am I doing? So really what I can think of is I have a line here, okay, that is all scalar multiples of v. So maybe here's v, and then tv is some vector out here. Okay. Adding that to p would be, so if here is p, adding tv to p would be done out here. Okay, so p plus tv would be, this vector. All right. Okay. So I didn't draw anything off the paper here. This is all I drew. So all the actions happening here on the paper. Okay, so anyway, geometrically then, this is like, really what you're doing is, instead of just adding two vectors like this, you're adding scalar multiples of a vector to another fixed vector, which gives you a picture that looks something like this. Okay, so then where does how does this relate to what you saw in differential equations? So there's the following theorem. So theorem, suppose ax equals b is consistent for some given b. Okay, and let P be a solution. Then the solution set of AX equals B is the set of all vectors of the form W, which is P plus V sub H, where V sub H is any solution to the homogeneous equation. AX equals 0. So, those of you that have had differential equations already will probably immediately recognize what it is that's going on here. If you haven't, well then now you will know when you see it in differential equations what it is that's going on in differential equations. So what this is saying, there's a reason why I used P before. The P is the particular solution and the V is the homogeneous part. So TV is the homogeneous part, P is the particular solution. So notice that I'm going to do a proof, not a proof of the whole thing, I'm just going to prove one direction. So note that A times W is P plus VH. So that is A times P plus V sub H. Okay? So this is A times P plus A times V sub H. Those rules that I wrote out at the end of class last time tell you this. Okay. What is A times P? Well, I was told that P is a solution to AX equals B. If P is a solution to AX equals B, then A times P is equal to B. So this is B plus, what is A times V sub H? V sub H is a solution of the homogeneous equation A times X is equal to 0, which means that A times V sub H is 0. This is B plus a 0 vector, which is B, i.e. W is a solution to AX equals B. So it's a solution to AX equals B, but is any solution of that form? So I won't do that direction, but it's actually not so bad. It's essentially exactly what we did in that example. Okay. All right. And so that's the idea here. This is nice because essentially what it says is that the solution sets for the homogeneous equation AX equals 0 and the general equation, the non-homogeneous equation AX equals B, is that they've been offset. They've been offset by this vector P. I use the P there because this is the particular solution. So you want to see an example of what this would look like in space. Of course, you know, if the dimensions are off, this is what's going on in some higher dimensional space. The idea is the green plane is the solution set to AX equals 0. The blue plane is the solution set to AX equals B, and the difference is that they are offset by this P. They are parallel solution sets offset by this vector P, this particular solution. Okay, so geometrically that's what's going on. That's why it's nice to think about this. From a practical standpoint, the reason why you have to get comfortable writing solutions in parametric vector form is because later on in the course we are going to have to do this. We're going to have to do this over and over again because a lot of the quantities that I ask you to compute are going to rely on you first putting the solution in parametric vector form. So you gotta know how to do that. Okay. All right. So let's continue on. Speaking geometrically, one of the important things we saw when we were thinking about the geometric meaning of linear combinations and spans is the following. It was a question of when you were considering the span of two vectors, or the span of three vectors, or however many vectors, there was a question of what kind of shape was produced, right? What did that thing look like? And we saw that it depended on the vectors, right? So if you had a span of two vectors, sometimes that was a plane, sometimes it was a line, and sometimes it was a point, right? If you got down to a really bad case. And so the idea is that it very much depended on the relationship the vectors had with one another. So the simplest example was if I had two vectors, and I considered the span of those two vectors. If those two vectors were scalar multiples of each other, then the resulting span would be a single line, right? And that I want to view as a degenerate case, we'll say, when you have the span of two vectors and it's not all that it could be. So in general, we want to consider when a span of some list of vectors has the highest dimension. Now, I haven't defined dimension yet, and we're not going to do that till later, till like chapter 4. But you already have some intuitive notion of what I'm saying. So if I have two vectors, I want those two vectors to span a space that has dimension 2. So I want them to span a plane. All right, and I want to know when I can do that. Okay, so I want to know when I can actually know when two vectors or some list of vectors span like a maximal in some way space. And the best way to do that is through, or the best terminology you can come up with to describe this is the notion of linear independence. Okay, so linear independence of vectors. This is a very, very, very important thing. In fact, I'll add multiple stars here because this is a very, very important thing to understand. So a set of vectors, we'll call them v sub 1 through, say, v sub p, and Rn is said to be linearly independent if the vector equation x sub 1 v sub 1 plus x sub 2 v sub 2 and so on all the way up to x sub n v sub n is equal to the zero vector, so that's a homogeneous vector equation, has only the trivial solution. Okay. So this has only the trivial solution. The set v sub 1 through v sub p is said to be linearly independent, or sorry, linearly dependent so it's said to be linearly dependent if there exists a non-trivial solution to this. So there exists weights c sub 1 through c sub p such that, of course, not all zero, because if there do exist weights such that what I'm about to say is true, but it's only the trivial ones, then I don't care. So if there exists weights c sub 1 through c sub p, not all zero, such that c sub 1 v sub 1 plus c sub 2 v sub 2 and so on up to c sub n v sub n is equal to the zero vector. Okay, so literally all I've said here is that, oh, sorry, I didn't use n here, I used p, that's fine. So these are through C sub p. Yeah, so all these last indices are p. So what I've said here is the following. Basically, here's the definition of linearly independent. And if it's not linearly independent, then, well, this isn't satisfied. That is, this vector equation has more than just the trivial solution. Okay. So if it has more than just the trivial solution, then necessarily there exist those weights that that are not all zero, because it's a non-trivial solution, that make this vector equation hold. So what is this thing called in this case? This is called the linear dependence relation. So if you have a linearly dependent set, this is called the linear dependence relation. Okay. All right. So this is going to yield yet another way that we can actually express a lot of the stuff that we're saying in terms of whether or not some given systems have solutions. So all of these questions that we've asked before about whether or not some matrix equation or some linear system has a solution can be recast as a question of asking whether or not some set of given vectors is linearly dependent. Okay. Okay. All right. Okay. So, how do I want to first explain what it is that's going on here? Let's say let v sub 1 be the vector 1, 2, 3. V sub 2 be the vector 4, 5, 6. And v sub 3 be the vector 2, 1, 0. Okay. So questions. 1. Is the set containing the vectors v sub 1, v sub 2, and v sub 3 linearly independent set of vectors? Okay. And if not, find a linear dependence relation between them. Dependence relation between them. Okay. So, 1. How do I figure out whether or not this thing is linearly, or whether or not this set is linearly independent? Well, by definition, they're linearly independent if this vector equation has only the trivial solution. So asking myself whether or not it has only the trivial solution is trying to figure out whether or not the associated matrix equation has a free variable or not, right? So in order to do that, I need to set up my equation AX equals 0 and do row operations, right? Like I always do. Okay. All right. So if I'm setting up row operations, or if I'm setting up this vector equation to answer this, all I do is set up AX equals 0, where A has columns that are those three vectors. Right. All right. This is just another way of saying that I'm setting up the vector equation x sub 1 v sub 1, right? So this is the same as vector equation x sub 1 v sub 1 plus x sub 2 v sub 2 plus x sub 3 v sub 3 is equal to 0. Right? Okay. So this is going to allow us to answer the question of whether or not I can actually find a linear dependence relation. So my matrix, or the augmented matrix for this system is A0, which I can write as 1, 2, 3, 4, 5, 6, 2, 1, 0. And last column is all zeros. Okay. So then after some row reduction, I can reduce this to just reading row wise here, 1, 4, 2, 0. I can zero out these two entries here, so I'll do that in one go. So this is 0, minus 3, minus 3, 0. And then the last row is 0, 0, 0, 0. Okay. So if I do this, notice that I don't have to go all the way to reduced row echelon form to answer this first question. Is this thing linearly independent? Okay, the answer is, well, no, right? Because just looking at this, x sub 1 and x sub 2 are not free variables, but x sub 3 is free, right? So x sub 3 is free. So ax equals 0 has infinitely many non-trivial solutions. Okay, and so this set of vectors is not linearly independent. Well, being not linearly independent is being linearly dependent. They are linearly dependent. Okay. All right. So, if they're linearly dependent, I need to find a linear dependence relation. So to find a linear dependence relation is actually to just finish what I was doing and find an actual solution. So to find a linear dependence relation, I just solve ax equals 0 for a specific solution. There's infinitely many. There's a choice involved there, so this is not a unique thing. I'm going to be able to find multiple linear dependence relations, which makes sense. It's some relation is equal to 0. Obviously, I can scale it as much as I want to, and I am going to get a bunch of different stuff here, right? Okay, so if I look at this thing I had before, there's the matrix I had before. I want to finish solving this. So if I further reduce that, so if I further reduce this matrix to reduced row echelon form, what I get is the matrix 1, 0, minus 2, 0, 0, 1, 1, 0. And then the last row is all zeros. Okay, and so the equation I get is x sub 1 minus 2 x sub 3 is equal to 0. And x sub 2 plus x sub 3 is equal to 0, and 0 is equal to 0. X sub 3 is free, right? X sub 3 is free. Okay. So the idea here is, I can immediately say x sub 1 is 2, x sub 3, x sub 2 is minus x sub 3, x sub 3 is free. I don't have to put this in parametric vector form. I can just leave it like this for now. And so what I do here is choose any value of x sub 3 you want that's not 0, right? If I choose x sub 3 to be 0, unfortunately all of my weights would be 0, and that would be a trivial solution. So I want to choose any x sub 3 that's non-0. So i.e. X sub 3 is equal to minus 1. I didn't have to pick that. But if I let x sub 3 be equal to minus 1, then a solution is x, which is 2 times minus 1, so it's minus 2, 1, and minus 1, right? Okay, which corresponds, I'm off the page, which corresponds to the linear dependence relation that is, remember the weights, the equation in question was this. So this was the equation in question. And so, in this case, this would correspond to the linear dependence relation minus 2 times v1 plus 1 times v sub 2 minus 1 times v sub 3. That should be equal to the 0 vector. Remembering what v sub 1, v sub 2, and v sub 3 are, you can check that this is the case. This is minus 2 times the vector v sub 1, which is 1, 2, 3, plus v sub 2, which is 4, 5, 6, minus v sub 3, which is 2, 1, 0. And this should be equal to the 0 vector, which is 0, 0, 0. Okay. And you can just immediately check that this actually works, right? Minus 2 plus 4 minus 2 is 0. Minus 2 times 2 is minus 4, plus 5 is 1, minus 1 is 0, and minus 2 times 3 is minus 6, plus 6 is 0, minus 0 is 0. Right, so this works out. This is the linear dependence relation. So note that as I said earlier, what is important here is that notice I asked some question about some new thing that I defined, linear independence. And when I asked that question, I said earlier in the semester that every single question that I asked, basically in this course, there's very few that this doesn't apply to, the answer is provided by me doing some operation, some row reduction of a matrix, right? Well, that's also true for linear independence. So note that for linear independence, to answer this question of whether or not a set of vectors was linearly independent, what did I do? I set up a matrix equation and I row reduced it, right? To answer the question of whether it's linearly independent, I didn't need to go all the way to reduce row echelon form. But ultimately, if I wanted to say find linear dependence relation, I just needed to solve a linear system. So all of these new terms, underneath them, right, under the hood, really what's going on is I solve a linear system. Okay. Yeah. So this is, I'm just checking that this works. So the question was that the actual linear dependence relation is this. So me writing this out is just checking that it works. Okay. All right. So that is, and of course I made this choice here. So before you ask, like, could I have chosen anything else here? Absolutely. So look at this linear dependence relation. Take it and multiply it by 10, right? So 10 times that whole thing. What do you get? Well, you get minus 20 v sub 1 plus 10 v sub 2 minus 10 v sub 3 is equal to 0, right? Is that a linear dependence relation for those? Absolutely, right? And that's 3 different weights there. So you You could have scaled this. That is a fact of what? Why can you do this? Don't tell me algebra, like I know why you can do it on this level, but the point is that going back here, if we had put this in parametric vector form, what would it look like? What would a general solution to this thing look like? Well, it would look like this. My general solution would be x sub 3 times 2 minus 1, 1. Right? And so any solution, right, to this homogeneous equation has to be a scalar multiple of the vector 2 minus 1, 1. Right? So in fact, me choosing x sub 3 equals minus 1 just made it the scalar multiple minus 1 times that vector. Me choosing to multiply this equation by 10 makes it minus 10 as a choice here. Okay. So that's why it works, tying in why the parametric vector form, or what the parametric vector form means for this. Okay, so anyway, I'll tidy up with all this stuff on Friday, and then we'll finish the chapter after that, talking about matrix transformation. So that's the plan. So anyway, I will see you all on Friday.